So hello, I'm back with another video that I'm going to talk about this book called Uncle Tungsten, and it's written by this guy named Oliver Sacks. And basically, just to talk about it, Oliver Sacks talks about his life as a young schoolboy back when he was in London, and how chemistry sort of affected his life, and how why is he interested in such like that. And if you didn't know, he's a very famous neurologist, and even though his profession is not chemistry, it's really something that really links him towards it. And so his Uncle Tungsten, is really it's really just a nickname, and it's just because his uncle really likes to work with tungsten, because he used to be working with light bulbs, and the filament inside the light bulb, well, that is tungsten. And that's why his uncle was called Uncle Tungsten, because he ran this factory trying to make light bulbs, and he sort of helped him introduce things with chemistry, just to get you guys forward. Now, back to the story that I was on. So basically, right now, young Oliver is trying to has his own lab finally, and he likes to make his own little experiments that he does in his own house. But sometimes this even attracts his older brothers, who have already graduated college and have not much to do when they're back in their house. But some of his experiments get a little bit out of hand, and this kind of makes his two older brothers decide that, hey, they kind of need to give him experiments kind of safer for the house. So the title of this chapter is called Stinks and Bangs. And by the title, you can already tell these are a lot about the chemical reactions that are happening. More of the interesting ones, some of the ones that have certain smells after, and some that have certain bangs. Yeah, I just told you what it was based on the title. Okay, so for some of the... Right now I'm going to tell you a lot of the experiences that we did, because the point of these videos, I try to make as much chemistry as possible with a little bit of the fun. So, one of the first experiments he wanted to do, because his brothers wanted him to start with something simple, was a hydrogen and oxygen reaction. And in this reaction, if you don't know, hydrogen and oxygen make water, which is H2O, hydrogen and oxygen. Now, because this is such a normal thing, the reaction is super great. And thus, when anyone is trying to mix these two, obviously a giant bang happens. And actually, you can even take water that you have, and if you were to separate the oxygen and just have the oxygen right inside a sort of glass thing, you'd be able to light a fire that's already put out and put it right back in, a little match, and you would be able to constantly relight the fire with the oxygen. Okay, for our second experiment, we have potassium perchloride with sugar. So in this experiment, basically you would mix the potassium perchloride in with the sugar, and what they would do is that they would have this like little pile right here, and once it settles, they would take a hammer and they would bang against it, and this would create a giant bang sort of noise, because by banging this hammer into it, the force has a little bit of heat, sort of, because of the energy that is put into banging it, and thus kind of mixes the potassium perchloride and the sugar together. And in this specific reaction, there's a bang sort of happens. Not from the hammer actually banging against whatever the mixture is under, but actually the mixing of these mixtures. So yes. And one thing that you might want to know is that when, similarly, when potassium perchloride and sugar is heated, and then you add a little bit of sugar in it, there is also another violent reaction that happens where you have like a little tube and you mix it together. Flames come out and it kind of becomes like a little purplish little thing coming out right out of it, and it kind of shows a little bit more of the reactions, showing that most reactions do need heat. And in this case, it kind of shows that the hammer banging against whatever it needs to, banging these two components together, shows that it contains heat when doing so. Moving on to the next one. Concentrated ammonia and iodine. So the molecular form of this is Ni3, or in other words known as nitrogen triiodine. So in this one, there is what happens is you have this like little, once you mix it together, you get this like sort of purplish paste, and once you paste it on like maybe a small sheet of paper, and you paste this like little stuff on it, the slightest thing can set it off. Not when it's all liquid, but once it dries off, a violent smoky sort of explosion happens here. And although it's not strong to like kill or be super dangerous, which is why several people, I'm sure if you search up on YouTube right after this video, the reaction of nitrogen triiodine, you can see several people have like taken a long stick maybe to get an approach, so then they don't actually, you know, get too close to it, because it is a pretty loud bang. Most people who have been doing it have been wearing some sort of ear protection and maybe some eye protection as well. Maybe even some facial protection might be good too, because you don't want to inhale some of those chemicals. And to sort of create this really loud bang, and then you can see like even the explosion of like purple stuff kind of leaving away, sort of like if there was a bomb that got soared off, you would still see a bunch of smoke coming out. But there is no fire, and this is one of those reactions that don't really need heat. So yeah. Or actually, it doesn't actually need like intense amount of heat. It's like it only needs like a tiny little tap. Like even like the smallest like little tiny mosquito or like fly that lands on it, it would sort of explode. But similarly, if you have the substance kind of just laying on a piece of paper here, or actually not even dried, if you have a fire going on down here, it will pop and like sizzle and like smoke out and have like a tiny amount. But it's good to put a tiny amount here, because if the explosion happens, you don't want to disturb whatever burner you have under it to cause a real explosion, and that wouldn't be good, would it? So yeah. Okay, on to the next one. So this one is ammonium dichlorate. Now this one has a little bit more complicated equation. That's nitrogen, hydrogen 4 twice, and then I believe chromium, oxygen 7. And just to double check my work, yes, that is chromium. And basically what happens is when you mix the dichlorite with this last part here, and also with the oxygen, what happens is you have this like little orange sort of pile, and once you add the dichlorite to it, you have this pile of ammonium, and you add the dichlorite to it, it sort of implodes on itself, and sparks start coming out here, and soon you have this like ash mountain with like orange stuff piling out, and it's very similar to volcano sort of kind of erupting. And at the end, you just get this like little pile of ash like right here. And this is just burnt out ammonium dichloride, the ending of the reaction. So yeah. And now I'm going to talk about a little bit more of the, a little bit more interesting things. So I'm not sure if you guys already know, but they are in the periodic table. Try to draw a little version of that. In the periodic table, there are like several groups in the periodic table. And here I'm just gonna draw a bunch of rough kind of sketches, kind of showing where they are based on my memory. And oh wait, no, I don't think that's that. Yeah, so we have like the noble gases. We also have the halogens, and then up here we have the non-metals, post-transition metals, metalloids. We're kind of in between non-metals and metals. And then we also have the transition metals, which is like your big bulk, which has like gold, silver, basically most of the stuff that you normally have. And then we also have alkaline earth metals, and then we have alkali metals. And I'm going to talk about alkali metals. Now, these contain, like, not many metals, I think only 6. And it includes lithium, like sodium, potassium, things like that. And basically, there is actually a way to dissolve these metals. And when I first thought about this, I thought it was quite surprising to see even, like, metals dissolving in the first place. So, yeah. The fact that metals can dissolve in the first place kind of shocked me. But, basically, what you could do is you can dissolve, these alkali metals into this, liquid ammonium. And basically what happens is, depending on which alkali metal you put, the liquid that comes out of the liquid ammonia will be different. For example, I believe if you put in sodium, you kind of get like a little bluish color. But if you put any other kind of metals, any of the other metals, you would get a different one. Like, I believe there's also, like, orange, and there's also green. Not quite sure which ones are which, though. But, yeah, and this is just one of the different things. Like, certain, specific elements have their own, like, kind of color when, given a certain reaction. Like, for example, I'll be talking a bit later, but oxygen with, what kind of flame it has, for example. So, yeah. This next one is magnesium. Talking about magnesium. And I'm not sure if you know, aluminum by itself, kind of the ones that you use in like cans, the ones that you have with your soda, or actually planes are also made of aluminum, is very reactive to oxygen. So like most pieces of aluminum have like this little thin protecting layer, so then any of the O2 that wants to get in doesn't actually destroy it. But assuming that there is something that did dissolve it, then it starts bubbling and it's violently reactive. In like less than like 5 minutes, you'll have this like big pile of like destroyed aluminum oxide just like all over the place, because kind of seeing how oxygen kind of destroys aluminum and how it's kind of like scary. Well, magnesium is very similar. It also is a very violent reaction, and so much so that they used it in bombs. And in these bombs, if there was like a bomb that would happen, like it thrown down in a specific place, after a while it would burn up right after the explosion. And why would they put magnesium on this? Is because this fire cannot be taken out by water nor sand, which they can't smother the fire because the fire would just constantly keep going with the sand or anything else. And I believe this is this fire can't even take out so much that if you took a piece of magnesium, you lit it on fire, and you threw it in water, it would actually burn in the water for a couple of seconds. And normally the fire gets put out, and it actually doesn't even get put out because of the water. It actually gets put out because it's already, once you lit the magnesium fire, it's already burning out the magnesium. And I'm sure you can find some videos on this as well. So yeah. And here I have another reaction. This one is called basically the burning oxygen one, which is the one I was trying to talk about earlier. And basically, if you try melting sulfur, if you have sulfur, and you try melting sulfur, so you have like a little fire here, and you try melting sulfur, and then you put the melted sulfur inside some oxygen. What would happen was you would notice that the oxygen would kind of flare up and would turn sort of a kind of like a bright blue sort of flame. And this is because of the heat of the melted sulfur kind of creates the heat for the reaction, kind of showing that reactions, most of them do need heat. And so this would kind of burn the oxygen, turning it blue. And like I said before, certain elements do have their own reaction, do have their own color, kind of when they're burnt or when they're melted or dissolved. So yeah. And then also, just a small quick one, there's one that's with chlorine and nitrogen. And in this, because the reaction is so great, whenever you put it in like a little test tube with whichever it's in, this test tube would actually explode when the reaction is in process. And this is one of these reactions that don't actually require heat. But because chlorine, if you look at a periodic table, only requires one valence electron to become full, but nitrogen, on the other hand, requires 3. If you put these two together, they would require only 4 in total, which means that they would be half filled with valence electrons. They would be half filled, and most atoms, or any reactions, what they want to go, they either want to be, most of the time, they either want to be full shells or half-filled shells. So basically, they either want 4 or 8 valence electrons. And so because it goes to 8, the reaction is very violent because it wants it very badly. And that's why most of the noble gases, since they have 8, they normally don't react with anything, which is like helium and like krypton and things like that. So yeah. And for my final one, I'm going to be talking about iron sulfide. And this is, I saved this one for last because it's one of my most favorite ones, kind of a little bit interesting. And so, basically in this reaction, reactions normally need heat to, like I've been saying constantly this entire time, usually need heat to be reactive. Now, when you guys were little, you probably had this like little reaction where you have the magnet, and then you have like the little iron filings that kind of get attracted by the magnets. Well, basically what you do, you take a bunch of iron filings, and then you mix it with some sulfide, and you will get this reaction. You wouldn't get a reaction, but you would have this like little pile. And you could easily separate it by taking a magnet, right? But if you were to heat this reaction, it would actually glow bright. And at the end, this new iron sulfide wouldn't actually be attracted at all, not even partly, to magnets. And this is something that kind of interested me, which when you react two different elements together, you a lot of the time some of the properties change, and they don't always mix, and they don't always get the same properties when they're coming back out. So yeah, this is the last one, and this is the one that really interests me. But please tell me what you think, and I will see you next time. Goodbye.